All right, the recording is started, uh, and class is started. Okay, perfect. Yes, it's the last week, Monday of the last week. Incredible, incredibly hype. Um, so quick announcements. As I've mentioned before, there's going to be a normal lecture today and tomorrow. There's not going to be any attendance polls for these lectures, so we are in fact done with attendance polls. But normal lectures today and tomorrow. You will be getting your final exam, or I'll be releasing the final exam on Wednesday, and then you will have until 11:59 p.m. Eastern on Friday to complete it. So you should have roughly 3 days to complete the final. As I said, I expect it to be similar in length slash difficulty to the midterm, with the caveat that now you have 3 days instead of an hour. Um, so hopefully that makes it easier. Yeah, in terms of an exam review kind of session, I was thinking today or tomorrow, both maybe, we could maybe spend some time going over any questions that you all have. So if you, uh, I guess I'll spend some time today at the beginning of lecture. If anyone has questions on any material like throughout the semester that you would like to review, we can do that. And then tomorrow, I figure I could mostly just dedicate the lecture to that. So if you want to come prepared with questions, um, yeah. So that's exam stuff. Um, as I mentioned, it's likely going to be there's going to be more points available than it's worth, and so there's the potential to, I mean, you can either think of it as like you can get over 100%, or you don't have to complete the entire exam to get 100%. I encourage you to try all of it anyways, just in case you don't do as well on a particular problem as you expected to. But it's probably going to be something like 60 to 65 points, and then it's going to go in the grade book out of 50. Um, so something to keep in mind. PA3 is out. It has been out. It is due on this Wednesday, which is the day after tomorrow. My standard spiel about that is there's a leaderboard. Feel free to engage with that. Uh, yeah, don't, I mean, don't yeah, do PA3, I guess, is what I want to say there. Oh, and the write up for that, the space for the write up for that is open on Brightspace. So if you did a write up, you can submit that. Also, problem set 6 has been released. Um, it is entirely extra credit, and it is worth the same as the other 5 problem sets. So each problem set is going to be worth 6%, and there's um yeah, each problem set's going to be worth 6% of your overall grade. So if you get 100 on problem set 6, that's a potential 6% extra credit. Oh, something about the late date for PA3 going past the end of class. That was just because I added 5 and didn't really think about things. Don't submit it that late. Um, I should maybe change the late date on that because okay, so I have to get grades in by the 6th. So um by August 6th, like which is Tuesday. So I would love it if I didn't have grades to recalculate on Monday night. Um that's what I'll say there. Uh please don't wait until Monday night to submit PA3. I'm not gonna like undo that. I'm not gonna change the late date at this point because that just feels mean. But like, yeah, I don't know. I would like to not have to think about this on Monday night. So I don't know. Do with that what you will. Um, everything else, problem set 6 is due Friday, the same time as the final, uh, and so on. Okay, that's all the assignments. Any questions on course stuff or logistic stuff before we move on to review questions? All right. Any review questions? Any topics over the course of the semester that you all would like me to maybe cover again or cover in more detail or cover in a different way or something like that? I assume you all spent the weekend studying. If you didn't, don't disabuse me of that notion. Low-key tuned out ever since we started graphs. That's super fun for you. AVL trees, I get how they work, but they confuse me a bit. Okay, we can talk about AVL trees. A left-right rotation. Okay. Okay. All right. I guess that's the thing we're doing is AVL trees. Um, find a good enough example so that I can kind of uh let's create a whiteboard. Oh yeah, here we go. Okay, can everyone see the whiteboard? Okay. So the basic idea of an AVL tree, actually maybe it's worth pulling up the lecture slides that I posted uh on Brightspace for this. Here we go. Okay. So the basic idea of an AVL tree is we maintain balance, right? AVL tree is we maintain balance while inserting and deleting, right? And so if we do this at every step, then at most we only ever have to shift the balance by one. Or I guess, okay, so maybe to recap, balance here is a property of the node. So the balance is the depth of the left, or maybe, I don't know, it's sort of symmetric, or it's like anti-symmetric, but you could say like maybe the depth of the right minus depth of the left. And so if we maintain balance after every single operation, then the balance of any given node is only ever going to change by at most one after an operation, which means we want things to be in the range -1, 0, or 1, because if it's like -1 or 1, then we can't really do any better, and if it's 0, then it's already balanced. Which in particular means that after an insertion or a deletion, the worst that's ever going to happen is like a 1 is going to turn into a 2, or a -1 is going to turn into a -2, right? So we need ways of resolving these particular cases. And then AVL trees are basically a huge switch case statement on what the tree looks like and how to sort of fix that, right? Um, so what do we, okay, so let me find this example. Yeah, okay. So the the example from the slides, which I'll just use here, is there's to rebalance, right? We have two operations available to us. We have a left rotate and a right rotate. The idea of a left rotate is I take a tree that looks like this, um, and I sort of I rotate it to the left, or I rotate it kind of counterclockwise around this node, and that turns it into a tree that looks like this. So A, B, C, like that. And then a right rotate goes the other way around, right? So this is maybe left, this is right. Yeah. And in doing so, we kind of expect the balance of these nodes, or sorry, the balance of these interior nodes to change, right? And so we can perform a sequence of left and right rotations to fix the balance, to kind of ensure that all of the balances are in the range -1 to 1. So for a concrete example, I'm gonna look at uh, a thing here. Yeah, okay. So maybe I'll draw out these examples. I'm just going to copy these from the lecture slides, um, which are in particular posted on Brightspace. But let's do this. So if my tree starts like um, this, so I've got something here, got something here, I've got something here, and something here. And let's say I insert a new node right here, right? If like before insertion, the balance here is we said right minus left, so the balance here is -1. The balance here is 0. Um, After insertion, the balance here is -2, and the balance here is -1, right? So this balance needs to be, I mean, this one is fine, but this balance needs to be fixed because it's a -2 now. So if it's a negative balance, that means the left side is too heavy, because we interpreted our balances as sort of going right minus left. Um, so depending on which way you look at it, right, it's anti-symmetric. But depending on which one you pick, either 2 or a -2 means it's either too heavy on the left or too heavy on the right. Um, one or the other. And so whichever direction is too heavy, and you want to rotate away from that, right? So we perform a right rotation on this, uh, and we end up with this instead. And now we've got the 3 children here, right? And now the green node gets added still on the leftmost child, right? So this now looks very nice, right? This has a balance of 0. This is a balance of 0. This has a balance of -1. Yep. That's a right rotate. It sort of works the same way if you rotated it the other way. I mean, if everything was sort of symmetric, like mirrored, you would do a left rotate. Sometimes you have to do more than one rotation, right? So you could have um, let me make sure I have, yeah, okay. So here's an example. So if we have a tree that looks like this, it's got something there. It's got, I'm gonna draw the children in boxes just so that I don't get confused. I've got a box there, I've got something here, and then I've got a box here, and a box here, right? Um, so the balance here is -2, the balance here is 1, the balance here is 0, right? And then the boxes are all leaf nodes, so we don't really need to compute a balance for them. Now let's say we insert here, right? This updates our balances. So this changes What does this do? This changes the balance of this one to be -1, right? It goes from 0 to -1. This changes the balance of this to be 2, right? And this changes the balance of this to be negative. Uh, wait. Oh, the balance of this was -1. Now it's -2. Yeah. Okay. Yeah. So in particular, here we've got this situation where there's two things that became unbalanced, but they're sort of unbalanced in opposite directions. Like this is a +2, this is a -2. So that suggests we're going to have to do two different rotates, right? So we start by rotating the lower one, and we rotate it to the left, right? So I'll rotate it. I'll maybe draw the rotation that we're doing. So we'll rotate this to the left. That was bad. There we go. That looks better. Okay. Doing that, this top tree remains the same, but now we get this node as the new root, right? And now it has a child like this, and it has wait, sorry. It has a child like this. Its other child goes here, and then we get something like this, and then we give it the green box right here. And then we need to, so once we've rotated this one left, we need to rotate the root, the original root to the right, right? Because if I recalculate the balances here, this is at 0, this is at well, I'm not going to compute this because it's a anyway, this is at 0, this is now at 3 versus 2, so this is at -2 still, right? So we rotate this to the right, which gives us this node becomes the new root, right? So it has two children like that. Each child has two boxes, and then our green inserted box goes right here. Or sorry, green inserted box goes right here. Yeah. Right. So now we can recompute the balances. This is at 0, this is at -1, this is at 1, and that's fine. Right. So the reason the AVL tree is kind of efficient is you can kind of cache the balances, right? So there's a couple things, like one, no need to recompute all balances every time, right? So they only change on the path from the inserted node to the root, right? And you can sort of immediately determine how they're going to change, because if the insert was on the right side, then the balance is going to go up by 1. If the insert was on the left side, the balance is going to go down by 1, right? So you can very efficiently in logarithmic time just like zip all the way up from the new node back up to the root and recompute all of the balances on the path. And then while you're doing that, you go, okay, this 1 became a 0, so I'm fine. This -1 became a -2. Okay, so I need to rotate it. Let me rotate it and fix it. You go up another step. And oh, this 1 became a 2, so I need to rotate it the other way. Okay, so I'll fix that. And then you just sort of like, so you can kind of do this like as you traverse back up, right? So this requires you to have like parent pointers or something like that, or write your recursion in such a way that you can kind of rebalance the tree as you return up the stack, or as you like pop up the call stack. But the fact that you only need to worry about the nodes on the path from the change back up to the root means that you can do this in roughly log n time, right? So you have logarithmic inserts and removals. Uh, no need to recompute all the balances every time. And then number two is if you stay balanced at every step, then each node only needs a constant number of rotations. Right. So we're never going to get into this situation where like the balance of a node becomes like six or something like that, to where we have to do like a whole bunch of like left rotates just to get it back in place. Right. Because the most that the balance is ever going to change is by one, because we're inserting one node. And after every operation, we rebalance. Right. So this allows us to also maintain the logarithmic complexity, right? If this wasn't the case, if we did a bunch of operations, if we like batched together a bunch of operations and then tried to rebalance the tree, then the balance at the node might not be constant anymore, right? It might be like the balance of the root might be something like n or log n or something like that. And so we have to do a number of rotations equal to the balance or proportional to the balance somehow, right? And so you would get some like extra factor here in front of that. And so it wouldn't be a log n time anymore, right? That's the idea of AVL trees. Does that make sense? Are there more questions about that or about anything else? Robert, are you satisfied with my left-right rotate? Yes. Okay. Wonderful. Arian, you're good. Anything else? Red black trees? No, I didn't cover red black trees. Any other questions? Any other uh, concepts that people would like me to cover or recover from the last 7 weeks? Yeah, I could go over Kruskal's again. Um, okay. Oh, by the way, did people watch the lecture videos that I posted? Or I don't know if you can call them lecture videos, but the videos that I posted implementing prims and Kruskals over the weekend. I guess one was on Friday, one was on Saturday. This is take two. Yeah. Well, take one didn't go well, and then I just deleted take one, and then I realized that I didn't need to say it was take two. But here we are. Anyway, yeah, we can talk we can talk about Kruskals. The 368 iceberg. Oh no. Um, oh wait, okay, sorry. Actually, that reminds me. Before I talk about the algorithm, thank you all for sending me some of the dankest memes I've ever seen. For the graph theory memes that I asked about for Friday's attendance poll. Um, these are incredible. I am gonna do my best to respond to every meme. Uh, drawing your meme out is honestly a vibe. It's good. Anti memes are also memes. I don't know. It's good. Okay, so cruise calls. Um, the idea is it's a or I'm not gonna. Okay, so it's a greedy algorithm for computing a minimum spanning tree. Right. So Minimum spanning tree is a subgraph uh, on the same set of vertices that is a tree and has minimal weight among all such subgraphs. Right? Now, actually, I've been lying to you. Um, so Kruskal computes like a minimum spanning forest, because for graphs for some graphs there might not exist a minimum spanning tree, right? And in fact, this is something that I do actually want to talk about here. So I'll say more about this in a minute. But this is the idea of Kruskal's, or that this is a minimum spanning tree that it computes. Greedy algorithm means at every step we take what looks like the locally optimal decision, and these locally optimal steps add up to be something globally optimal, right? Um, so uh, actually, maybe it's worth writing that down. So greedy algorithm, take a bunch of locally optimal steps, right? Um, okay, so the locally optimal steps that we take, the thing that we're trying to optimize for is minimizing the sum of the weights of all the edges. So at every step, we pick the edge with the smallest weight, right? So Kruskal's. So uh, while I misspell while there are still edges unpicked, uh, pick the min weight edge, right? Um, if uh, pick the min weight edge, call it E. If adding E creates a cycle, throw it away. Otherwise, add it to our forest, right? And that's it. That's the algorithm, right? So we have our like greedy thing, which is at every step we pick the edge with the minimum weight. And you can sort of show that because you're doing this, it is impossible for there to be a spanning tree with a smaller total weight. Because if there were, then at least one of the edges, then you could get that spanning tree by swapping out an edge for something of lower weight. And if that were possible, then we would have picked that edge instead. So this is the greedy part. The fact that we pick the minimum weight edge every time. And then here we just sort of ensure that it remains a tree, or I guess forest. The like the the hard I don't maybe I don't want to say hard part, but like the the thing about this algorithm is you need to know whether adding E creates a cycle, right? Um, or whether it creates a cycle in the like undirected reduction of the graph that we're building, or in particular whether adding E causes the spanning graph to no longer be a tree, right? So that's what I mean when I say creates a cycle. Um, uh, and so there's a couple different ways to do this part. Pick an appropriate color, right? So there's like the naive way, which is you build the graph, or like you add it, run DFS to detect a cycle, and remove it if there's a cycle, right? Um, and then there's the sort of the galaxy brained way, um, which is using a union find, right? So every time, so each here each vertex is its own set, um, an edge u to v means we union the vertices u and v, and then don't add an edge, let's say u to w, if find u equals find w, right? So every vertex starts disconnected in our tree. Every time we add an edge, we mark those vertices as connected, and the union find data structure basically ensures that the connectedness relation is transitive. And we don't add an edge if its endpoints are already connected, right? And this way we sort of ensure that at every step it remains a tree. Does that make sense? Sorry, I realize I'm saying things like transitive. If you haven't taken discrete math, transitive means, or I don't know, maybe people know what transitive means, but transitive means that if R of AB holds and R of BC holds, then R of AC holds, right? So if A and B are connected and B and C are connected, then A and C are connected. Then A and C are sort of implicitly connected via this pair, without having to explicitly mark them as connected. And the union find data structure takes care of that. So we kind of like automatically get all compositions of all edges for free. Transitive is less dumb than the other properties in that class. Okay, yeah. I mean that's fair. Like anti-symmetric things. I don't know. Question about the approach. What's up? Forums? Give me a moment to Google this, please. Typo. Oh, prims, prims. Okay, prims. So this is not what prims does. Prims starts at a vertex and grows the tree from that vertex, right? So uh Kruskals is kind of greedy on the set of edges, right? Like we pick the min weight edge at every step. They're both looking for the lightest edge in some sense, but they're looking at them in different orders, right? So in maybe it's useful if I give you a counterexample, which is actually a thing that I wanted to talk about anyways. So consider the following graph. Um, right. Here's a graph, perfectly good graph. Um, I can run Prim's algorithm, right? Actually, let's get 6 edge weights. Why not? Someone shout out 6 numbers. 12, 7, 29, 24, 16, and 1. Perfect. Okay. So we can run prims here. Or if we run prims here, right? Let's say we start at this vertex, right? So we keep track of a set of picked vertices, right? is the empty set, and the unpicked vertices is all the other vertices, right? So we find the so at each step we find the closest vertex in V minus S and add it to S, right? But in particular, saying closest vertex implies that it must necessarily have a finite distance, right? So if we start here, the next vertex we'll pick is this one, right? So we'll add this edge. So uh, let's color the spanning tree that we build in green, right? So we add this vertex with this edge. Okay, now what's the closest vertex? Well, it's this one because it's the only one reachable from our set of picked vertices, right? Okay, so we'll add this edge. And now we're done because every other vertex, or no, sorry, we're not done. Oh, I'm so dumb. Okay, I missed this one. Okay, so we add this one. Great. And now we add this one because it's at a distance of 16, right? But now we can't add this because this vertex, the distance from the set of picked vertices to this one is infinite, right? Because we have to grow out from where we started. So prims may not find a spanning tree if no spanning tree exists. Kruskal's, on the other hand, um, starts by picking. So let me draw the graph that Kruskal generates in orange, right? So Kruskal starts by picking this edge. It doesn't care about the vertices, right? It starts by picking this edge, then it picks this edge. So in picking this edge, it grabs these vertices. In picking this edge, it grabs these vertices. So 1, 7, then it picks this edge. And so it adds in this vertex, 1, 7, 12. Then it wants 16. It won't take 16 though, because 16 connects two vertices that it's already taken, right? So if like this edge would uh, connect two vertices that are already taken. So it won't take 16. It won't take 24. It won't take 29. Yeah, it goes 1, then 7. Exactly. Right. So the output of Kruskal's, the output of Prim's is this tree that spans like a subset, or it spans like a subgraph, right? And the output of Kruskal's is not a tree at all. It's a forest that collectively spans the entire graph, right? And this is essentially the distinction that I wanted to make between the two, anyways. Um, oh yeah, seeing them drawn out is definitely better. Um, but yeah, like if there is no spanning tree, Kruskals will find a spanning forest. If there is no spanning tree, Prims find a will find a tree that spans the subgraph on the vertices reachable from the start vertex, right? So, um, yeah, that's what I want to say. Like, if the graph is undirected, then this doesn't matter, right? Because if the graph is undirected, then if it's connected, everything's reachable from everything else. Like if it's connected, it's strongly connected, right? Um, so Prims in theory could give you an incomplete tree. That's right. The thing that Prims produces might not touch every vertex, right? Because Prims just stops when it can't find any more vertices to add. But that could mean that all the remaining vertices are not at a finite distance from the tree that we've been growing. Kruskal's will always give you the full forest, yes. The other side of that though is even if that means every node is a tree on its own. Yeah, exactly. But in order for that to happen, that means Kruskals doesn't pick any edges, which means that there are no edges to pick. Right. So if you run Kruskals on a discrete graph, it'll give you back a discrete graph because what else are you going to do? If you run Prims on a discrete graph, it'll just give you the vertex that you started with. Right. But Prims guarantees that it's guaranteed to be connected, right? So it guarantees that the spanning graph that you produce is connected, right? Or that the graph that you produce at the end is connected. Kruskal's, it might not be connected. Way back, we had an attendance poll about tree balances. Okay. And how we wouldn't bother balancing if it was 3 or -3. Go on. So it's not so much that we don't bother balancing if it's 3 or -3. It's that we never get in a situation where we have to balance a 3 or a -3, right? Because if every balance is, I mean, maybe I can go back up here, right? Um, so if every balance is -1, 0, or 1, if we start with a balanced tree, that means every balance is one of these three values. Then by adding a new node or by removing, like by adding or removing a single node, the balance is only ever going to change by 1 or -1, right? Which means the maximum it could end up is if we go from 1 to 2 or from -1 to -2. So we're never like, there's no way to get a balance of 3. So we don't actually have to worry about what happens when we get a balance of 3 because it's just not going to happen. Yep. Any other questions about ABL trees or about MSTs or any other things that we talked about in class or that we didn't talk about in class that you wish we talked about in class? I'm happy to spend the rest of the lecture doing this, just like doing a review. Um, if not, maybe you want to like think about questions and come back tomorrow with questions. Um, that works too. Okay. To avoid sitting here silently for the next 15 minutes, I am going to start talking about Matroids, uh, because none of you can stop me from talking about Matroids. Um, if anyone has a question, you will stop me from talking about Matroids by asking that question. So, uh, I don't know. I mean, you can you can interpret that as a threat or as a pro. I don't know. All right. Let's talk about Matroids. I'm gonna create a new whiteboard for this. Okay. So, um, a Matroid is a combinatorial structure that shows up in optimization problems. Optimization problems. Sometimes. In particular, if the optimization problem that you care about contains a matroid, then it means the greedy algorithm is going to be optimal. Right? So our minimum spanning tree problem, right, is an optimization problem, right? So we have a constraint, which is that the graph has to span everything, or that the graph that we pick has to span the original graph, right? And we have an objective function, which is the total weight of all of the edges that we've picked. Um, and so we want to minimize the total weight of all of the edges subject to the constraint that it spans. Um, And so this is an optimization problem, and you can show that the problem contains an instance of this structure called a matroid, right? Uh, so maybe before I um, maybe let me give you an intuition for the proof of why Kruskal's is optimal, and then we'll sort of see where matroids kind of naturally fall out of this, right? So theorem, Kruskal's produces a spanning forest with minimal weight. Right. I should disclaimer, this is not on the final. So it like yeah. Anyway, okay, Kruskal produces a spanning forest with minimal weight. Um, let's prove this, right? So um I am going to consider uh a very simple case here, right? Which is we're looking at an undirected graph and our undirected graph is connected, right? So consider a connected undirected graph. Actually, I don't need to consider a connected undirected graph. Okay. So there's three parts of this that I have to prove, right? Forest, this is easy. Um, spanning and minimal weight. So maybe I'll say this is proof obligation one, two, and three, right? So one, it's spanning because if it weren't spanning, if it weren't spanning, that means there's a vertex that we haven't touched. Either the vertex has an edge adjacent to it or incident to it. If there's, uh, um, then there exists an edge we haven't picked. And this edge is currently unpicked, and because it's incident to a vertex that hasn't been touched, it's guaranteed to be picked at some point, right? Because this vertex is going to be in its own unique set in the union find, and so it's in particular not already going to be connected to the other endpoint of the edge. So once we're done picking all of the edges, we're guaranteed to span, right? That's easy. Two, it produces a forest, right? At every step, we ensure it's a forest. And I mean, I don't know, finite graph. So we can just use induction, right? It's a forest at the first step. If it's a forest at the ith step, it's going to be a forest at the I plus one step, and it's a finite graph, so there's a finite number of edges, so induction terminates. If you had an infinite graph, maybe it's like countable. You can use like transfinite induction or something like that. This is not a discrete math class, so I don't want to talk about that. But okay, minimal weight. This is the interesting part, right? This is where we use the fact that it's a matroid. Um, okay, so suppose there was a better forest somewhere, right? So suppose we picked a set of edges, right? So maybe this is the output of Kruskal's, and there was, um, let's say this was a better forest, right? So um, yeah, maybe the weight of this one was bigger, right? Better forest in terms of like a smaller forest, right? Something with a smaller weight. So I'm trying to prove this by contradiction, right? I'm trying to show that there cannot possibly be a forest with a smaller weight than the one that Kruskal outputs. right? So if there were, that means that there's some edge. So let's say F is the forest, the output of Kruskal's, and I'll call F prime is better than F, right? This means that there's some edge in F prime that we picked that we didn't pick in F, right? If it's a different forest, that means it contains at least one edge that we didn't pick in Kruskal's, right? Um, and furthermore, it means that the weight of uh, what do I want to say? Okay, I actually am going to start with connected undirected, right? So that the only thing I have to worry about are trees, right? So in particular, let me just replace these with t's. T prime, t prime, and t, right? Because every tree on the same number of vertices has the same number of edges, right? If you've got n vertices, that means you have n minus one edges. So the size of T prime and the size of T are the same, like the cardinalities are the same, which means if T prime contains an edge that T doesn't have, it has to go the other way around as well, right? I'm going to call it, so E prime is an edge in T prime, but not in T. And then this means that we necessarily have some E in T that's not in T prime, right? So we can think of going from T to T prime by swapping out at least one edge, right? So we get rid of one edge and add another one, right? At least one. So in this example, we get rid of this edge and add this edge, right? So let me label this as this is T prime, right? So we can always think about getting from Kruskal's output to whatever this hypothetical best possible forest is by replacing an edge. Now, if we replace this edge and T prime is better, right? That means necessarily that the weight of E prime is less than the weight of E, right? Because we know that the sum of the weights of like I for I in T prime is less than the sum of for I in T, the weight of I, right? And the only difference here is like they have everything else the same, but this is like a bunch of stuff plus the weight of E prime, and this is a bunch of stuff plus the weight of E, right? And so this is like everything else is the same, so these cancel out. So like if we just start by assuming that there's a single edge that we're swapping, everything else canceled out, and so we know that the edge that we added to T prime has to be of a smaller weight than the edge that we added to E. But if it was a smaller weight, that means we would have visited. Um, this means that Kruskal's visited E prime first. It visited E prime before visiting E, right? Um, if it visited E prime before visiting E, but we know that it didn't add E prime, right? Because if it had, because E prime is an edge that we've sort of by construction assumed is not in the tree that we output from Kruskal's. Um, this means that the endpoints of E prime were already connected. And in particular, this means that they were already connected not by E, right? Because we haven't even visited E yet. So the endpoints of E prime are connected in a graph that contains neither E prime nor E, right? Which in particular means that in T prime, the endpoints of E prime are double connected. Where this is not a technical term, this just means that there's two things connecting them. So T prime is not a tree, which is a contradiction, right? Because we assumed that there was some better tree, right? So in particular, this shows that there cannot possibly be a better tree because if there were, we would have found it, right? If there was anything better, this algorithm would have found it because we necessarily visit the smallest edge each time. Do the vibes of this proof make sense? Perfect. Okay. Uh, so you can sort of think about like the key thing that we use here in the proof. The reason this works and like a greedy algorithm in general might not work is this exchange property, right? The fact that we can view other like um, other solutions, we can view other solutions as coming about by exchanging a pair of edges, right? Or by like exchanging something in our solution set. Um, and this is exactly what Matroids encode, right? So definition, a Matroid on we'll say on a ground set E. And the reason I'm calling this E is because the Matroid in this example is going to end up being the set of edges, right? So a Matroid is uh, is a um, maybe I'll just say a family of subsets of E such that actually maybe I should so I is a bunch of subsets of E, right? Um, such that the following conditions hold. Number one, the empty set. Okay, so the way of saying this is it's like a we call these independent sets, right? So this is like a rule. This is like a rule for saying when some S is independent, right? So yeah, so given a set of edges, a matroid is a rule for saying when that set of edges is independent, or given a set of things, it's a rule for saying when the set of things is independent, such that the following three conditions are satisfied. So number one, the empty set is always independent. Number two, if A is independent and B is a subset of A, then B is independent, right? So this suggests that independence is something that gets broken when you add too much stuff, right? So if I've got some set that's independent, then removing stuff from that set is it's necessarily still independent, right? And then this is kind of the important one. Um, so if this is the exchange property, so if A and B are both independent, and without loss of generality, say like the cardinality of A is greater than the cardinality of B, then there exists some X in A minus B uh, such that A minus such that B union X is independent. Okay, so this basically says that if you've got two independent sets where one is bigger, then you can always move one element from the bigger one to the smaller one and have them still be independent, right? And in particular, this means that all maximally independent sets have the same cardinality, right? Because if they didn't, then you could move something, or you could keep moving things until they have the same cardinality. So this is a matroid. One example. Oh, it's 942. So you can leave if you want. Uh, I'm gonna give examples of matroids maybe on Tuesday, or I don't know. If people want to stick around, I can give examples of matroids now. Okay, cool. I'm gonna give examples. Djokovic versus Nadal is over, so I'm free. I don't know who that is. I'm sorry. Okay, so one example. Oh, the Olympic match. Okay, very nice. Okay, so one example is um, a graph, right? E is the set of edges, and a subset of edges is independent if it contains no cycles. Right? So the empty graph or the sort of discrete graph with no edges contains no cycles necessarily. If you've got a graph with no cycles, you can remove an edge and it's still not going to have any cycles. And you can sort of see if you've got two graphs with no cycles on the same set of edges, then you can like move one edge to the like from the bigger one to the smaller one and have there still be no cycles. Um, just because the like a tree always has n minus one edges, right? So you can always add an edge. If you've got n minus two edges, then you've still got like one edge that you can add and have there not be any cycles. Okay, so this is an example of a matroid. In particular, this is the matroid that we use for Kruskal's algorithm. Um, Another example is a vector space. So if you've taken a linear algebra class, maybe the idea of independent sets kind of makes sense in this context. So E is maybe the set of vectors, and then a subset of vectors is independent if it's linearly independent, right? So if no vector can be achieved as a linear combination of the other vectors, right? Uh, and then maybe the last thing I'll say is if you have some okay, so a very general problem, right, is we have some function from our set E to maybe the real numbers, and we want to find some uh, S subset of E such that um, S is uh, maximal with respect to inclusion, S is independent, and we want to minimize the the total weight of all the things in S, right? So the claim is that if this is our problem, then an algorithm that always works is set S to be the empty set. And then while there exists something in E minus S that we can add, uh, pick pick the thing with minimum weight, right? So and just keep doing this. And then at the end of this, S is necessarily gonna satisfy all of these conditions, right? And the proof for this, like the reason that this always works, uses somehow this third exchange property, right? Which says that if there was a better S that you could have found, then you would have visited the like if there was a better S somewhere, then you could move something from the S you found into the better one, and that means that there's something that you would have visited before, and so you would have already found that better one, right? It's the same idea as the proof of Kruskal's, except it's just like it's axiomatic, right? Um, and so a lot of times, in fact, I think I want to say every time you have uh, an optimization problem where a greedy algorithm works, you have a matroid. Okay, thanks for sticking around. That's all I want to say about matroids.